If you've ever dealt with networking cables, you know the deal with copper. It's just a tangled, power-hungry mess.
Hmm.
And for cable TV, coaxial has always been the standard, sure, because it can handle data going both ways, but it just completely fails over any real
It
distance.
really does. Your signal just degrades.
Yeah, every few hundred feet, you get more noise, the picture gets muddy. It's a real problem.
And that's exactly what this deep dive is for you, the listener, who needs to get a handle on long-distance coaxial and its necessary jump to fiber optics.
So we're looking at a specific piece of hardware today.
We are the Thor Broadcast F-RFoF-TXRX. And the core idea here isn't just that fiber goes farther. The real trick is how you perfectly replicate a low-frequency, bidirectional, high-bandwidth electrical signal and turn it into light.
Something fiber really wasn't originally designed to do.
Exactly. So the whole mission of this device is to mimic what copy does, that bidirectional RF communication, but over single-mode fiber. And that extends the range up to, 10 kilometers?
It's basically teaching light how to carry this huge, complex analog signal without losing any fidelity.
And that bidirectional part is key. It means you can't just use one fiber. The system needs two separate communication paths running at the same time.
Okay, hold on. That makes sense on the surface, but why a whole second fiber? If you're converting it all to light anyway, couldn't that small amount of return data just sort of piggyback on the main path?
That is a fantastic question. And the answer is that the data needs are just. They're radically different.
How so?
So think of it this way. First, you have the forward path. That's the 100-lane superhighway, right? Goes from the head end, the cable company's office, out to you.
And that's carrying all the TV channels.
All of them. Channels 2 through 135 on that high-frequency range, 45 to 1,000 megahertz. It needs enormous bandwidth.
Okay, and the second path, the return.
That's more like a dedicated service road going the other way. From your modem back to the head end. It's for data, for interactive services.
Like clicking on demand or your internet packet.
Exactly. And it uses a much narrower frequency, just 5 to 42 megahertz. So by keeping them on two separate fibers, you get the absolute best quality and lowest noise for both. No interference.
So the devices themselves, they're constantly converting that electrical RF wave into an optical signal and then right back again in both directions.
Simultaneously. Which means compatibility is a huge deal.
Well, it has to work with everything.
And it does. The sources confirm it's basically a universal translator. It works with Comcast, Spectrum, Xfinity, you name it. It supports encrypted CATV, clear QAM for the digital HD channels, even old analog standards.
And looking at the specs, I saw something that really stood out. The input signals have to be incredibly precise before they even hit the laser. It says input level of 80 plus or minus 5 dBV.
Yes.
What happens if you're off by just 1 dB?
The whole thing breaks down. That input leveling is absolutely essential for a clean conversion to light. If the signal's too strong, you distort the laser. Too weak, and you're just amplifying noise.
So the system is a pair. You have the FRFoF-TX, which sends the forward path and receives the return, and the RX does the opposite.
They work in tandem over those two fibers, yeah.
And the connection itself is also super specific, which, again, points back to this constant battle against noise.
You're talking about the connectors, the SKey APC.
Yes. What's the deal with that?
That APC is everything. It stands for angled physical contact. Most normal connectors are flat, and they can reflect a tiny, tiny amount of light back down the fiber. It's like a light echo.
And that creates noise.
Unacceptable noise, yeah. The angled connector completely eliminates that reflection. It's what ensures you get that high fidelity over the full 10 kilometers.
You know, that isolation, the fact that light can't carry electricity, it offers a pretty unique benefit beyond just extending cable service. The sources mention it can act as a fiber break.
Right, for secure areas.
For like a SCIF room.
Exactly. For a sensitive compartmented information facility, you need to break any conductive path. A copper cable could potentially be tapped electrically. By converting the signal to a non-conductive light path, you've created an inherent layer of security.
It's just a different medium.
And at the end of the day, that functional advantage of using two dedicated fibers is it's profound. You get high-quality, ultra-low noise transmission over these huge distances, supporting modern TV, fast internet, and even a robust security.
It really is astonishing when you consider the engineering involved. The entire multi-gigabit flow of your data and entertainment hinges on that one electrical signal being managed to 80 plus or minus 5 dBV before it's even turned into a stream of photons. It makes you wonder, How many other modern utilities, things we never see, rely on a perfect continuous translation between electrons and photons just to deliver our daily data? And it raises a question. When we talk about data speed, are we actually talking about the speed of light, or are we really talking about the precision of the translator? Something to think about.